here's another idea.
Let's start with that. Now, even if you can't remember exactly how to do that, what's the machine that's going to make all parts of this work? What are you going to have to, do?
Row reduce.
Yeah, row reduce. So you don't wait for me. Just start row reducing, get it down to reduced echelon form. Actually, you don't even have to get it down to reduced echelon form. All you have to do is get it down to echelon form, but you might as well just get it down to reduced echelon form anyway. That's a rank that looks like a V. So the machine that makes this go is row reduction, get it down to reduced echelon form. So by this point, actually, we're already in echelon form. Then we just keep going till we get it to reduced echelon form. At least I did. And so we see a pivot position here, a pivot position here, and a pivot position here. Okay, so we need a basis for the row space of A. Now that we have our matrix in reduced echelon form, what do I do?
Find the bases.
Well, right, but how? They're on the blackboard somewhere. Where do I look for them? Okay, let me just remind you. They're just the non-zero rows of your reduced echelon form. So since we're looking for the row space, it's going to be, it'll be vectors in R4. Here's one, here's one, and here's one. So 1, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1. That was pretty straightforward. Just take the non-zero rows of your reduced echelon form. Non-zero rows of the echelon form would also work. We might as well just use reduced echelon form. I mean, do it either way. Okay, basis for the column space of A. Where do I look on the blackboard for those?
Isn't it on the diagonal?
Nope.
Non-zero columns.
So not quite. Which columns do you have in mind? Because all these columns are non-zero.
Do you do the pivot points, but then go back to the original matrix?
That's right. That's exactly right. So we look at the pivot positions. I have a pivot position here, a pivot position here, and a pivot position here. But I can't use the reduced echelon form in the matrix because every time I do a row operation, the column space actually changes. The row space stays the same, but the column space changes. So I have to go back to my original matrix, and these tell me which columns to take. Take the first one, the second one, and the last one. So 1, 1, 2, 1, 2, 3, and 1, 1, 3. And together, those three vectors span the space that all four of these vectors span. But these are linearly independent, which makes them a basis. So go back to the original matrix, not for the row space, but for the column space. For the row space, use your echelon or reduced echelon form. For the column space, go back to the original matrix, and the reduced echelon form will tell you which columns to take. And of course, the number of vectors here and the number of vectors here will always be the same. They'll always be the same because both of these are going to have the same number of vectors as the number of pivot positions. So for C, we have to do a little bit more work, but we've done most of the work already. And basically for C, I have my reduced echelon form matrix. 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, and then vertical bar is 0, 0, 0. So this first row says x1 plus x3 equals 0. The second row says x2 equals 0. And the third row says x4 equals 0. So I have one free variable, that's x3, the only column without a pivot position. So let's let x3 equal t, x2 is 0, x4 is 0, and x1 is minus x3, so x1 equals minus t. And so x1, x2, x3, x4 is minus t, 0, t, 0. In other words, t times minus 1, 0, 1, 0. And so a basis for the null space is this. Minus 1, 0, 1, 0. Every vector that this matrix kills is going to have that form. When I say kills, I mean sends it to 0. And part B, what's the rank of the matrix? This is like a 2-second problem. You have to remember what rank is, and you can just look on the board because it's there.
Three.
It's 3, yeah. It's just the dimension of the row space, the column space. They're the same. It's the number of pivot positions. The rank of that matrix is 3. It's the number of vectors in a basis for the row space. It's the number of vectors in the basis for a column space. It's just the number of pivot positions. In this case, it's 3. And remember that the rank plus the number of vectors in like the dimension of the null space, since this is the number of pivot columns, and this is the number of free variables, the number of columns without pivots, this plus the number of vectors here is always going to add up to the total number of columns. There's 1, 2, 3, 4 columns. 3 plus 1 is 4. So this ties together a bunch of stuff. Are there any questions about any of this? If you can do your row reduction, the rest of it's easy. Oh, that matrix that I just erased, the original matrix A, which is still in your notes. What would you say to me if I asked you if that matrix was invertible? What should you say to me? You should say to me thumbs up.
Yes.
No, you should say something else.
No.
You should say something else.
It wasn't a square matrix?
It's not square. It could possibly be invertible. Only square matrices could possibly be invertible. This was a 3 by 4 matrix. Say A is a 10 by 10 matrix. And let's say I tell you that where the row space, where a basis for the row space has 10 vectors. Say A is a 10 by 10 matrix where a basis for the row space has 10 vectors. How many vectors are in a basis for the column space?
Isn't it 10?
10, yeah, absolutely. Basis for the, I just basically told you that there are 10 pivot positions. So the basis for the row space has 10 vectors, basis for the column space has 10 vectors. If A times X equals 0, what can you tell me about X? If X is a vector in R10 and it takes it to 0, what can you tell me?
Is it 0?
It has the only vector that this can go that this matrix can take to 0 is the 0 vector, because we know that the dimension of the row space, the dimension of the column space have to be 10. Therefore, the dimension of the null space has to be 0. The only vector that we can take to the 0 vector is the 0 vector. What can you tell me about the determinant of A? Just be a little careful. What can you tell me about the determinant of A? Let's come back to that in part B. I'll ask a different question first. In part C, let me ask you this. Is A invertible or not invertible?
A is invertible?
It is invertible. Absolutely, it's invertible. Its rank is 10. The only 10 by 10 matrices that are invertible have rank 10. So what can you tell me about the determinant of A, since it's an invertible matrix?
That it's 10?
No.
No.
You can't tell me exactly what it is. What can you tell me that it's not?
0.
Yes, not 0. So you don't know exactly. It could be anything else based on the information I've given you so far, but it can't be 0. The only 10 by 10 matrices whose determinant are 0 are non-invertible. Let's see. We've already talked about rank. What can you tell me about the columns of the matrix A? What property do they have? There's two things you could say here. One of the things you could say has one word and the other one has two words. And they're both true.
Is it spanning?
Yeah, they definitely span. They're also linearly independent. Same with the rows.
The rows are also linearly independent.
And spanning, yeah.
Okay.
So remember the invertible matrix theorem. For a matrix, all of these things have either are all true or they're all false. So the columns are spanning and they're linearly independent. The rows are spanning and they're linearly independent. I know that because this matrix has a what did I say originally? Its row space is 10-dimensional. That basically, since its basis is 10-dimensional, I basically just said the rows are spanning. So the columns automatically are. So if I gave you a matrix where this wasn't true, all this stuff would be false. There'd be other vectors which go to the 0 vector. A wouldn't be invertible. The determinant of A would be 0. There wouldn't be 10 vectors in the basis for the column space of A. If the rank was anything smaller than 10, none of this stuff would be true. Okay. Let's see. Oh, one more thing I should ask you. G follows F, not C. The reduced echelon form of A is, what do you get when you row reduce A since it's an invertible matrix? So if it's an invertible matrix, it has 10 pivot positions. If it has 10 pivot positions, what's the reduced echelon form of A? There's really only one possibility.
Your identity?
The identity, right. It's I10. So is this, let's let A, how about we have 1, 1, 1, 1, 2, 3. 2, 3, 5. Is A invertible? Now, this time it's square, so I'm not pulling your leg. It could be invertible. Might not be, but it could be. Is A invertible? If so, find A inverse. So basically, to find out if it's invertible, you're going to row reduce this and see if you get the identity or not. But to find its inverse, you'll row reduce it. So 1, 1, 1, 1, 2, 3, 2, 3, 5. But you'll start with the identity over here. 1, 0, 0, 0, 1, 0, 0, 0, 1. Row reduce this. If you get it down to the identity, it is invertible. And you'll see your inverse over here. If this has anything else, if it's row reduced form, if it's reduced echelon form, is anything else besides the identity, it's not invertible, you can just say it's not invertible. So go ahead and row reduce this. Get it down to reduced echelon form if you can. Maybe it's possible, maybe it's not. If it's not, it's just not invertible. Oops. That's right. What are we doing? More stuff? So we can already tell this thing is going to be invertible. We can already see this thing in echelon form. We have a pivot position in every row, in every column. That's why a non-square matrix can't be invertible. It can't possibly have a pivot position in every row and every column. Let's see. So 1 minus 2, 0, 0. So 1 minus 2, 1, 3 minus 2, minus 1, minus 1, 1. So here, assuming you haven't made any mistakes, is A inverse. And we can see if we have made any mistakes by trying to take A and multiplying it by A inverse. So if we take the original matrix, 1, 1, 1, 1, 2, 3, 2, 3, 5, and multiply it by 1 minus 2, 1, 1, 3 minus 2, minus 1, minus 1, 1. Let's see what we get. If this is the inverse, if this really is the inverse, I should get the identity. So let's see. So I'll take my fingers out. 1 plus 1 is 2, minus 1 is 1. Minus 2 plus 3 is 1, minus 1 is 0. It's looking good so far. 1 minus 2 is negative 1, plus 1 is 0. 1 plus 2 is 3, minus 3 is 0. Minus 2 plus 6 is plus 4. Minus 3, 4 minus 3 is 1. 1 minus 4 is minus 3, plus 3 is 0. I mean, also, already this is looking great. It'd be hard to believe that I get this far and found a mistake later. 2 plus 3 is 5, minus 5 is 0. Minus 4 plus 9 is 5, minus 5 is 0. And 2 minus 6 is minus 4, plus 5 is 1. Yep. We got it. So as soon as we saw that the left-hand side was going to have the identity as its reduced echelon form, we knew it was invertible. We just had to keep going to figure out what the inverse was. is that a subspace of R2? All the vectors where both the first and the second component are positive. What are the three things I have to check to see if it's a subspace? What are the three things I need to check to see if this is a subspace?
Do you need to check whether it's closed under addition and scalar multiplication?
And what's the third thing? Third one's the easiest one. You've given the two hard ones. Some specific vector has to be in there. Which is the special vector that has to be in there?
Zero vector?
And the zero vector, exactly. So is the zero vector in there? So this is certainly greater than zero, and this is certainly greater or equal to zero, and that's certainly greater or equal to zero. So this is definitely an S. That's the first thing we have to check. We have to show that it's closed under scalar addition. So if let's say V equals V1, V2, and W equals W1, W2 are in S, that tells me that V1 is greater than 0, greater than or equal to 0, and V2 is greater than or equal to 0, and W1 is greater than or equal to 0, and W2 is greater than or equal to 0. That's what it means to be in this S. It's basically just all the vectors which are in the first quadrant, including the axes. All the vectors whose first and second components are both non-negative. So V plus W is V1, V2 plus W1, W2. And this is V1 plus W1, V2 plus W2. So if V1 is greater than 0 and W1 is greater than 0, what can you tell me about greater than or equal to 0? What can you tell me about V1 plus W1?
They're also greater than 0.
Yeah, V1 plus W1 is greater than or equal to 0. And since V2 and W2 are greater than or equal to 0, V2 plus W2 is greater than or equal to 0. So this thing is certainly in S. So it's closed under addition. And last, is it closed under scalar multiplication? If I take a vector whose first and second components are non-negative, and I multiply it by a constant, is what I'm going to get always going to be non-negative? The answer could be yes or no. Which is it?
Could you repeat the question, please?
Sure. Let's say V is in S. So V equals V1 and V2. where V1 is at least as big as 0 and V2 is at least as big as 0. And let's say C is a real number. Is CV necessarily an S? If I take this vector and multiply it by C, do I get another vector whose first and second components are non-negative? Right, I see you shaking your head, and I hear you saying, no, yeah, not necessarily. So actually, it turns out that 3 is no. We didn't have to write all of this. All we had to do is find one counterexample. So the answer to this is no. The answer is no. All we have to do is write a counterexample. So 1, 1 is an S, and -1 is a real number, but -1 times 1, 1, which is -1 minus 1, is not an S. So it's not closed under scalar multiplication. And the rest of this is, I mean, these would be the 3 steps we'd have to do if we wanted to show it was true. It turned out to be false. When you're trying to show something's false, all you have to do is give one counterexample. When you're trying to show something's true, you have to show it's always true. So it's definitely not true, because this is an S because both its components are positive or non-negative. But if I multiply by a number, here is an example of a number where I could multiply it and it's no longer in S because one or both of its components are not non-negative. Now they're both negative. How are you all with finding, we've done this recently, how are you all with finding eigenvalues and eigenvectors? Is that okay? See a thumbs up there, thumbs up there. So yeah, that's recent stuff. Let's see. What other skills do you need? I think between the review we did last time and the review we did this time, that's most of it. Any questions? As I said last time, I will have office hours next week and the week after. They won't be my regularly scheduled office hours. Look on my webpage. If you don't see anything there that works for you, contact me, and I will set up a Zoom meeting with you. And hopefully by the time you take your exam, all your questions will be answered. I will post the exam at the beginning of the exam week. You'll have 3 hours and 15 minutes to do it and upload it to the usual place. It will be on our webpage. You can use a calculator if it helps. I mean, I don't know if that's going to help, but you can use one. It's closed book, closed notes. If there's a problem that you encounter while you're going through there, the problem with the exam itself, please feel free to let me know. And I think that's it. So I was very pleased to hear about the announcement that we will be open next semester, even though we'll still be under severe restrictions, but it will be lovely to see you back on campus, for those of you who will be back on campus. And I will see you then, and I will see many of you virtually before then. So some of you I'm going to see in 14 minutes, when we really have to have get a move on and start right on the hour. Bye, everyone.
Thank you.
My pleasure.
Thank you. Bye.
Bye now.